Saxon Algebra 1, Lesson 81. Congratulations, students. We are now 2/3 of the way through Algebra 1. There are 120 lessons in all, and we have completed 80. Woo! Pat yourself on the back. That is a lot of work. We still have some challenging lessons in front of us, but soon we will kind of tip over the top and start in on some, I don't want to say easier lessons, but less intense. So that is exciting. We are not going to go hard all the way up to 120. Somewhere around lesson 100, we will definitely take a little step back and you will feel, I think, less intensity in the lessons. So 20 more hard ones to go is what I'm saying. It's still a lot, isn't it? Okay. We have been talking about solving systems of equations. To solve a system of equations, we have already discussed two different ways to do it. Not only discussed, but we have talked about it. I've shown you how to do it, and you've worked a bazillion problems. We can use this thing called substitution, where you basically reshape one of the equations so it fits into the other, and you solve it that way. Another strategy is called elimination. And that is where we set up the two equations so that we can add them together and one of the variables will cancel out against the other. We can multiply to make that happen, but we set it up so that one of the letters will eliminate. Today, we are going to discuss the third way to solve a system of equations, and that is by graphing. Now, I will give you spoilers that there are some neat advantages to graphing, but there are some pretty big disadvantages. So we're not going to spend a lot of time doing this. We're going to show you how it works, tell you why it's good, tell you why it's not so good, and move on fairly quickly from this. I am going to tell you that when you get to advanced mathematics, the final year of high school mathematics that John provides, we will learn two more methods. But for this year, substitution, elimination, and now graphing is what we will cover. Oh, just a second. I have my second notebook buried under my first. There. Okay, so let's talk about how to graph. I'm just going to tell you what they are right now. The pros of solving by graphing is that it's super easy. You don't have any new technique to learn, and it's very visual. It gives you a really nice picture of what the solution looks like. The con, and this is huge, and this is why we don't use it often, is that it yields an imprecise, hi Gracie. Gracie's come around for a bit of petting. Hello, sister. Hello, sister. I'm petting her, sorry. Algebra has to wait. Good girl. That's because if I don't pet her, she'll beat me up. She'll hit me with her foot until, you know how dogs are. They demand. Cats are the same way. Good girl. I need to talk about solving by graphing. Can you be patient a few more minutes? It's getting close to that time of day, where we go outside and do things. Good girl. Stay right there. It yields an imprecise answer, and that's why we don't like it. Okay? Substitution and elimination, as well as these other two that we're going to get to, they give very precise answers, and that's why we prefer them. This is nice if you're trying to understand what you're doing and you want a visual picture of it. Remember that in order to graph, we always want to get an equation into this form where m equals the slope, and I want you to be sure to copy all this down. If it's a positive slope, the little car is going up the hill, and we measure the rise over the run. The run always goes to the right, the rise goes up. If it's a negative slope, then we measure the first step as the sink, and that's going down. The run always goes to the right. B is the y-intercept. It's the place where our line crosses the y-axis. We always graph this first, and then from this dot, we use the slope as a treasure map to help us find the second point. Then we connect the 2 points. So we graph the y-intercept first, we graph the slope second. That's counterintuitive because they come up in the opposite order, but whatever, we just have to cope. Okay, let's actually do one of these problems and see what happens. Example 81.1. And it says solve by graphing. That's John's instruction. Okay, fair enough. And then he gives us what now looks pretty familiar, a system of equations. And because John is a buddy and a pal, he has put these into beautiful y equals mx plus b order. This is a system, so it's got a little bracket around it. We see that these are in pretty good shape, aren't they? Except this one has no slope. Oh, well, let's see. If there's no coefficient, we can always put in a 1. And if there's no denominator, we can always put in a 1. Okay, so that does have a slope. It was just invisible. It's 1 over 1. Kind of hard to see. All right, so what I'm going to do is I'm going to draw us a nice rectangular coordinate system. I'm going to graph the first one in orange. So I graph the y-intercept first. I go to this value on the y-axis. And it's positive 1, so I put my first dot right there. Then from the y-axis, I use the slope as a treasure map. I go up 1 and over 1. I'll say it's about there. There's my second point, and now I'm ready to draw my line using one of my technically precise straight edges. I mean, it works. Okay. As long as I've got the purple marker handy, I'll use that. I'm going to do my second one in a different color. That'll just help me keep the picture straight. I start with the y-intercept. It is positive 4, 1, 2, 3. So I need to go up to there to make my first point. Now I'm ready for my slope. Oh, my slope isn't a fraction, but that's okay. I can make it one. It's a negative slope. That means it's a sink over a run. So I go down 2 and over 1. Interestingly, I find myself putting the purple point right on top of the orange point. Huh. That's interesting. Let's see what that means. Oh, it's not perfect, but pretend it is. What that means is that the solution for this system of equations is right here where the 2 points cross. And in this particular case, we can see that it is point 1, 2. It's easy to see that because that is such a nice, even solution. And look, my picture doesn't even make it look that perfect. That's why this solving by graphing is so fussy. It's really nice to see, oh yeah, the solution lies at the point where the 2 points intersect, or intersect is the better word. Where they cross, that point is the solution. That's the value for x and y that will make both of them come true. And if we wanted to, we could plug x equals 1, y equals 2 into both of these, and they would both come true. It would be a beautiful thing. So that's really lovely. We get the clean visual. It was certainly easy because all we had to do was graph the lines. We didn't have to learn some new technique, right? Like substitution and elimination. You have to learn new techniques of algebra to make it happen. We already know how to graph a line, so we just graphed 2 lines and looked at the place where they crossed over. It was easy. It's super visual. We can see it. And in this case, it gave us a precise answer, but in another case, it might not be so handy. All right, remember that when we're graphing, we always want to be in this form, and John won't always be so kind as to set it up for us perfectly. Example 81.2. Solve by graphing. Our system of equations looks weird. This does not look like the proper format, does it? It looks very skimpy and short on details. But let's just plow ahead and see what we can find out, see what we can do. Y equals 2. What that means is that no matter what x is, y will always be equal to 2. So we go right here to 2 on the y-axis, and we can draw a line like this. No matter what x is, y will always be equal to 2. And I'm just going to label that line to make sure that we remember what the names of these lines are. Okay, I'm going to do the other one in green here. This one I did in orange. Y equals x. Okay, well we can do this one as a system of equations. It's 1 over 1 is the slope, and b is 0. So we can convert this into this format. This one's a little harder to convert. We could do it, but it would just be confusing. This one's not too confusing. We can put in the slope of 1 over 1, and we can add plus 0. That means our y-intercept is 0. So I'm going to go right there to start. Our slope is 1 over 1, so I go up 1 and over 1. And now pretend it's perfect. I get this, and I know that this point right here is going to be the point where x and y are both 2. This is x equals 2. Now, my graph is sloppy enough that you can't really see that. See how I had to make that one much bigger to get it to work out? Already, my graph has made it imprecise. But I know that if y has to equal 2 and y also has to equal x, then our point... Oh, I wrote this wrong. This is y equals x, right? I was thinking that this is true, but this is the name of that line. I know that the place where they intersect has to be 2, 2. That's the place where y equals 2, and that's the place where y equals x. They have to be the same. So this is our answer. Already, my graph was a little too imprecise to read that, but I can easily think it out based on how simple those equations were. Let's try, oh, we're gonna do a third, okay, those are the two examples we're going to do of equations that we can, systems of equations that we can solve by graphing. This one had pretty normal equations in it. These were kind of weird. Now what we're going to do is look at systems of equations that give us a very strange looking picture. Instead of having our nice little intersect, like we did in these first two where we had a nice little dot that connected them, we're going to deal with some weirdos. Okay, here's our system of equations. Looks harmless enough, right? The y-intercepts look fine. We notice they don't have slopes, so we can fill that in. And what we notice is, oh, look, the slopes are the same. That's kind of interesting, right? We'll see what happens when we graph that. Okay, I'll do the first one. We go to positive 2 on the y-axis, and then we go up 1 and over 1. Up 1 and over 1. There's my second point. And there's my line. I'm going to call it y equals x plus 2. Now I'll go to graph the second one, and I think I'll use pink. This time we start at -1, so that's down here. And we go up 1 and over 1. So my second point is there. Look what happens when we draw the line. These two lines are parallel. So let's make some notes about this. The lines are parallel, not coincidentally. The slopes are equal. Whenever you have equal slopes, you will have parallel lines. Think about it. The fact that these slopes are the same means that they're running at the exact same angle. This pink one's a little crooked. It bothers me. Right? Those two are exactly equal. They're like the two rails on a railroad track, if you've ever seen such a thing. And they will run along at the same angle forever. They have different y-intercepts, so that's why they aren't the same line. But they're never going to touch or cross. And so what we can say because of this is there is no solution to this, right? If the solution is the place where the two lines cross, there's no solution. And we have a fancy name for this. These are called inconsistent equations. Okay, that's the fancy name. These are the properties of inconsistent equations. They represent parallel lines, their slopes are equal, and therefore there is no solution to this, meaning there's no place where the lines are ever going to cross. Now let's try another weirdo. John's going to give us a variation on this, which is actually kind of nice. This time, he gives us a system of equations. It's the same one, isn't it? Plus 2 and minus 1, yes. But this time, he doesn't want us to graph it. He just says, determine whether the following set of equations have a common solution. Well, we already know this, but we can do it again. Let's put in the slopes. Now, whenever we see matching slopes, we know we have trouble. Same slopes. Means that we have parallel lines. And that means we have no solution because these are, again, what we call inconsistent. And another way to say it, before we said it was they were inconsistent equations, we can also say this is an inconsistent system of equations. Those two expressions mean the same thing, but I wanted you to see it written both ways so that you wouldn't weird you out if it was different. Okay? So, we noticed it just by looking, but here's another way to determine. Another way to see if a system, has a solution. And this is pure algebra. Do you notice how both of these are equal to y? We can use substitution to say that they're equal to each other. I'm going to ignore these little slopes, and I'm going to say, well, if y equals x plus 2, and y equals x minus 1, 1, then x plus 2 should be equal to x minus 1. And we know, we can see right from the get-go, that's not going to work. Let's subtract 2 from both sides, and let's subtract x from both sides. The x's drop out, and we get 0 equals minus 3. I don't think so. So that tells us right away that there's no solution. That's another way to come to the same conclusion as we did up here. As soon as we saw the slopes were the same, we knew we had trouble. Here's another way set the two equations equal to each other and try to solve it and see if you get something that makes sense. All right, and the last one. We're going to learn another fancy phrase. This time, rather than talking about inconsistent equations, we're going to talk about something called dependent equations. And again, we could also call this a dependent system of equations if we wanted. Two expressions that mean the same thing. And here is our example. All right, so John would like us to determine if these two equations are going to have a nice solution, like a happy, healthy system of equations. So what we notice right away is that these guys are not in proper shape, so let's fix them up. This one, I can just add x to both sides, y equals x plus 2. This one, let's see, I'll add the 2x, so then I'll have 2y equals 2x plus 4. And then to get that y by itself, I'll divide everything by 2, and that gives me y equals x plus 2. Wait a minute. Now look at our two equations. Once we simplified them, we discover they are exactly the same. We call this equivalent equations, which is another way of saying they're the same. And once we determine that they're equivalent equations, we call them dependent equations. It's just another way of saying the same thing. And we know that the important thing here is that they are actually the same stinking line. They're the very same line once you simplify. And so John gives us another example where he asks us to test and see whether the following set of equations is dependent. He does not ask us, wait, this is the very same one. We already did this one. Okay. He does not ask us to graph this. He asks us to determine. The best way to start to answer his question is to get them both into y equals mx plus format, which we already did up here. He gave us the very same one, so whatever. This would be y equals, oh, I'm sorry, I wrote this wrong. Y minus x equals 2, so it would be y equals x plus 2 once we swim that across. And then we would do the same thing, I just did it, but I'll do it again. I'll swim the 2x to the other side, and then I'll divide everything by 4. And I get y equals x plus 2, and I go, wait. That actually ended up being the very same thing. They're equivalent equations. That means these are dependent. It's a dependent set of equations, a dependent system of equations. We can use any of that language. I'm just going to write dependent. And that's our answer. Okay? Now, what I'm going to do is I'm going to recap the 3 different kinds of systems that we just looked at. And I'm going to do it by drawing simple pictures. Okay? The first kind of equations that we looked at just intersected. Let's pretend those are the 2 lines. They just intersected. They had one point of solution. That means they just crossed in one point. And there's a fancy word for this. We call these equations consistent. They're just normal, happy, reasonable line systems of equations, and these are the kinds we spend most of our time with. Then we had two little weird freaky children, didn't we? The first one was when the lines run parallel to each other, right? We said that was because they had the same slope. If you have the same slope, then you have parallel lines and they'll never cross, so there's no solution. So we write here, these are parallel, and there's no solution. And we call these inconsistent. And then this last little weirdo that we dealt with, let's make it go like this. We were graphing what we thought were two lines, but they ended up being the exact same line. Now, if I'm drawing the exact same line, you shouldn't be able to see any difference, right? But I'm making this thicker to try to show, here, just a second. I want it to look like it's two lines in the same place. We really wouldn't be able to see that we wouldn't be able to see two separate lines, but I'm trying to help you see. This is the same line. So there are infinite solutions because every single point on here solves both equations. So we write infinite solutions. And the fancy name for this is dependent. It didn't fit on one line. I was so hoping it would. All right. Consistent is what we're used to. Inconsistent is parallel. Same line is dependent. Three fancy words that John will use in the homework. He'll ask you questions about it. Make sure you have this graph handy and you can connect it to the picture, the important parts of the picture, and then the fancy word that goes with it, all right? He does ask questions about this. And he summarizes it nicely on page 334, if you ever want to just look in your book. Okay? Oh wait, there's one more. And this is very similar to what he asks in the homework. Consider the equations y equals 2x plus 5 and y equals x. Is this pair of equations consistent, inconsistent, or dependent? Okay, let's work backwards. If they're dependent, that means that when you simplify them and arrange them properly, they're exactly the same line. So let's look and see if there's any work to be done. No, these are all perfect, right? It's y equals, they're in y equals mx plus b format. These look good, right? We could add a plus 0 here if we wanted, and we can add a 1. We can give both of these slopes 1 if we want to. We don't have to. But we can see there's no way that these numbers are going to come out to be the same. They're different, so it's not dependent. What about parallel? If it was parallel, they would have the same slope. I'm going to write that here too, because that's just super helpful information to know. And we can see these don't have the same slope. This is 2 over 1. This is 1 over 1. So they're not the same slope. So that tells us they're not inconsistent, and that means that they must be consistent equations because they do not fit the profile of the outliers. So these are just two happy little equations that we could graph if we wanted to. John doesn't ask us to. And they would give us 1 point of solution, and that would make us happy. This is solving systems of equations by graphing. That is another thing that it's good for, is it's very useful for finding inconsistent or dependent solutions. Now, in our real math life, our regular math life, we don't really run into these very often, so it's not a big deal. But solving by graphing is a great way to see when these strange situations pop up. Okay, guess what? I'm done. Goodbye.